So, hello everyone again. This is lecture number 9 from the chapter Work, Energy and Power. This may be the last lecture. In this lecture, we will be studying in the further discussions on collisions. So, let's start directly. I'm Samir Lawankar. This is lecture number 9 of Work, Energy and Power. Let's begin our discussion. So currently we are on the last topic of collisions. In this chapter, in this concept of collision, we will first in the previous discussion we have already understood about the elastic and the inelastic collisions. Let's move forward with that. Let us now understand the mathematical representation. First, we will understand for 1D frame, that is 1D motion, 1D one dimension, and then we will end up the discussion with 2 dimension with some of the examples. Okay. So let's begin. So we have already started with collisions in the previous lecture only. So these all things are completed. So we have finally understood that what is elastic collision and basically what is inelastic collision. So if there is some deformation happening and that deformation is not relieved, then basically that is called like inelastic collision. Otherwise, if the complete, let's say we visualize it as a compressed spring and the complete deformation is relieved, then we say it as an elastic collision. Okay. Please remember one more thing, that if in the question it is given that it is a completely inelastic collision, then what happens? Then the two particles move together after the collision. Okay. So basically, let us suppose that this is a mass M1 and this is some mass M2. Let us suppose M2 is at rest and M1 is moving with this velocity towards this. Then if it is supposed to be a completely, if it is supposed to be a completely inelastic collision, then what we can say that the masses M1 and M2 will move on with some of the velocity. Okay, we'll find out that velocity Bf in the subsequent mathematical calculations. Okay, so let's start the understanding of the mathematical formulation here. Okay, so consider first a completely inelastic collision in one dimension. Okay, so what happens in inelastic collision? The two of the masses goes together with some velocity. Because we are considering one dimension, in the figure given here, we can assume that the values of theta1 and theta2 is equal to 0. Okay, because we are understanding that it is in one dimension. So basically, after the collision, both will move in this direction only. Okay, that thing being said, let us understand the formulation now. So here, first of all, let us first conserve the momentum. So momentum conservation. Okay, so if we conserve the momentum, what do we say? We say that initial momentum is equal to final momentum. So if the initial momentum is equal to final momentum, what we can say? We can say simply, what was the initial momentum? It was m1 into v1i plus m2 into v2i is equal to m1 into v1f plus m2 into v2f. So I hope it is clear. We are just adding the momentum of both of them first initially and then at the final. As we know that v2i is 0, therefore this can be directly omitted to be equal to 0. And we also know that v1f and v2f are equal. Correct? Why? Because it is saying that it is a completely inelastic collision. Fine. Therefore, what we can write? We can write m1 v1i is equal to m1 plus m2 into v2 f, or not v2i, we can directly write it as only vf, because as both are same only, so we can write it as directly vf. Okay, therefore just dividing both the sides by m1 plus m2, what we can get? We can get what is the final value of velocity? Final value of velocity is m1 upon m1 plus m2 into v1. Okay, so this is the first equation we got. So basically we got the final value of velocity in terms of the masses and the initial value of velocity. Okay, so this is the first equation which we got here, right? Now let's move forward and let us now calculate the value of kinetic energy. Okay, so I think first step is clear to you. So basically what we did, we just calculated did the conservation of momentum. Okay, Now let us calculate the loss in kinetic energy. Okay, so there would have been some loss of kinetic energy because it's a inelastic collision. We know that in inelastic collision what happens, let us say we visualize it as springs, and if we use it as compressed spring, we can see that the deformation is partly revealed. Okay, so there is some deformation already happening, and hence you can also say that the initial kinetic energy is lost. Okay, therefore let us now calculate the value of delta k. So what is delta k here? It is basically initial value of the velocity. Here, why we are calculating initial minus final? Because we need to get the answer in some sort of positive value. So what is the initial value? It's half m v half m1 v1 I square plus similarly half m2 v2 I square, which will give you 0 only, minus half into m1 m1 plus m2. So it's m1 plus m2. Because the velocity is same, we can directly use it like this. Okay, we can also write it as half m1 vf square basically minus half m1 vf square minus half m2 v2 vf square, which can say then equal to minus half m1 plus m2 vf. Okay, now just using this equation 1, we can just write in the place of vf, we can write it as m1 plus m2. Therefore, this is nothing but equal to half m1 v1 I square minus half of m1 plus m2 into m1 square upon m1 plus m2 whole square into vf square. Okay, so I hope it is clear how we got this formulation. So just now I'm doing just mathematical inputs, mathematical formulation is being done. So finally after this, when you will solve it, you will get half m1 v1 I square into 1 upon basically multiplied by m2 upon m1 plus m. Okay, or in more general sense, it is nothing but half multiplied by m1 m2 upon m1 plus m2 into v1 I square. So this is the loss in the kinetic energy observed. Okay, so you can remember both these. I suggest to remember both of these. So please remember, for a completely inelastic collision in one dimension, what is the final velocity? If the initial velocity is 0 for m2 and final initial velocity of m1 is v1i, then the final value of the velocity for both of them will be equal to m1 upon m1 plus m2 into v1. Similarly, what will be the kinetic energy loss? The kinetic energy loss will be equal to half m1 m2 upon m1 plus m2 into v1. Okay, so that thing being said, which is a positive quantity as expected, so it's a positive quantity because there is a loss happening here. Okay, fine. That thing being said, now let us understand the elastic collision. Okay, again what we need to do, we first need to conserve the momentum, then we will conserve the energy. Okay, so let's start. Only simple mathematical formulas are being implemented, nothing very highly complex things are being done. Okay, let's go again very slowly. So using a nomenclature again, so basically we are doing it for one dimension only, so it's theta 1 equal to theta 2 equal to 0. So the momentum and the kinetic energy conservation equations are what? Okay, so first of all let us use momentum conservation. So momentum conservation. Okay, so for momentum conservation, what we can write? We can write simply that m1 v1i plus m2 v2i, which is the initial momentum, is equal to final momentum. It is m1 v1f plus m2 v2f. Okay, I hope it is clear. As the value of v1i is 0, v2i is 0, we can directly put this value as 0. Therefore, now what we can write? We can write it as m1 v1i is equal to m1 v1f plus m2 v2f. Okay, so I hope this first in momentum conservation is clear to you. Now similarly, let us conserve the energy. So energy conservation. So if we now conserve the energy, what we can write again? There is nothing but half m1 v1i square, because the velocity of v2i is 0, we can directly omit it and write as equal to half m2 v2f square plus half m1 v1f square. Okay, half can get cancelled directly. So therefore the equation which we got is half v1I square is equal to m2 v2f square plus, or write it in linear fashion only, m1 v1 f square plus m2 v2f square. Okay. So now I'm just doing some mathematical formulations here. So what I'm doing, please understand. So multiplying equation 1 with v2f. Just multiply equation v2f on both sides and then do 1 minus 2. So when you do this formulation, what you get basically is m1 v1i into v2f minus v1i, which is equal to m1 v1f into v2f minus v1. Okay, so what I basically did, I just multiplied v2f here and I also multiplied v2f here. So that said, m2 v2f square and m2 v2f square gets cancelled actually, and the thing remaining is which I just wrote here. Okay, do more simple calculations. Take out v2f common from both the sides and put it on same side. Let us say I put it on left hand side. I'll get v2f into v1i minus v1f is nothing but equal to v1i square minus v1f square. Okay, if you see clearly, we can apply the identity here, that is a square minus b square. Which identity I'm applying here? I'm applying a square minus b square is equal to a plus b into a minus. If I apply this identity here, so basically this and this can get cancelled, and the thing which gets left is v1i plus v1. Okay, so I hope it is clear. Therefore, what is the final formulation we got? The final formulation we got is the v2f, that is the final value of the second mass velocity, is nothing but equal to initial velocity plus the final value of initial velocity. Okay, so I hope we understood this equation very clearly. Now what we do, we have some formulation. Let us say I equate it as equation number 3. This was basically our equation number 1, that which was conservation of momentum. This was our equation number 2, which was your conservation of energy, and this is the equation number 3, which we just formulated using some mathematical formulations. Now let us put this equation in the equation number 1. So what we will get, basically we will get m1 v1i is equal to m1 v1f plus m2. In the place of v2f, what we can write? We can write v1i plus v1f. Okay, so now do more simplification here. Let us take v1i as constant on this direction, so we can get this as equal to m1 minus m2. Take v2f as constant here, so we will get here m1 plus m2. Okay, so therefore we can write this should be v1f. Yes, now it's correct. So now we can write v1f is nothing but equal to m1 minus m2 upon m1 plus m2 into v1i. Okay, so I hope it is clear how we get this equation, that is v1f is nothing but equal to m1 minus m2 upon m1 plus m2. Similarly, what we can do now, to calculate the value of v2f, we can basically apply this value of v1f in this equation here. So basically when we do this, it's v1i plus v1f, and therefore what the answer we get is, it is nothing but equal to 2m1 upon m1 plus m2 into v1. Okay, so I hope this complete mathematical formulation is clear to you, how we obtain these different final velocity formulas in terms of m1. What is we got in terms of m1, m2 and v1i. Okay, here m2, basically v2i was free, basically it was 0, therefore we obtained this in this form. Please also remember this is done for elastic collision, and similar formulation is already implemented for inelastic collision just before it. So this was the final velocity in terms of for inelastic collision, completely inelastic collision, and this was the delta k in this form for completely inelastic collision. And currently we just formulated the values of velocities, final velocities of v1f and v2f for elastic. Okay, so I hope the complete methodology being implemented to calculate is clear to you. Moving on, thus the unknowns V1F, V2F are obtained in terms of the knowns, which is M1, M2, and V1F. Okay, special cases of analysis are interesting. So let us understand some special cases now. So let us suppose in the case 1 that the two masses are equal. Okay, so that means M1 is equal to M2. If M1 is equal to M2, then what we can say? We can write V1F is what? V1F is basically M1 minus M1 upon M1 plus M1 into V1F, correct? Which will give you the answer as equal to 0. Similarly, what is V2F? Basically, V2F will be nothing but equal to 2 into M1 upon M1 plus M1 into V1F. So I'm just putting the values here. I'm trying to calculate. Okay. So if I just put this will cancel this, and therefore the thing which is remaining is this. So what does it say? It basically says that let us suppose this was some mass which was M, and this was also some mass which was M. It was moving with some velocity, let's say denoted as v1I. Okay, so after the collision has appeared, then what will happen? Then this will happen that the mass which was second, this will start moving with some velocity which is equal to v1I only, and the mass which came here will be put at rest with the velocity equal to 0. I hope you understand what is happening in completely elastic collision. Okay, so it is written here also. So it is saying basically the first mass comes to rest and pushes off the second mass with its initial speed on collision. Okay, so it basically says that the first mass comes to rest and the pushes of the second mass with its initial speed on collision. I hope it is clear to you. Moving on, now let's understand the case 2. So in case 2, what happens? It is given that M2 is very, very greater than 1. So basically what we can assume that M2 plus M1 is approximately equal to M2. Okay, so let us understand that scenario also here. So as we know, what is the relation? It is V1F, which is nothing but equal to M1 minus M2 upon M1 plus M2 into V1I. Okay, so if you look at this equation clearly, if M2 is very, very greater than M1, then what we can say? We can basically say that M1 minus M2 will be approximately equal to minus M2. Correct? Let's say M1 is 5 kg and take 5000 kg. So 5 minus 5000 kg is minus 4995. Correct? And that minus 4995 is approximately equal to minus 5000 only. Right? That's only being implemented here. So basically, and similarly, M1 plus M2 is also equal to approximately M2, right? Therefore, what we can say? We can simply say that V1F is nothing but equal to minus M2 upon M2 into V1I. So M2 getting cancelled, so this is equal to minus V1I. Similarly, what is V2F? V2F is basically 2M1 upon M1 plus M2 into V1I. Okay, so if M2 is very, very greater than M1, then this value will be very, very large, right? This will be very, very large, and this value will be very, very small. So if it is very, very small, it is very, very large, we can approximate this to be equal to 0. Okay, so because let us say for example, M1 is, let's say, 0.1 kg. Okay, and let us say M2 is something in sort of, let's say, 10,000 kg. Okay, so then what will happen? The mass will be something, it's 2 into 0.1 upon 0.1 plus 10, 1, 2, 3, 4, 1, 2, 3, 4, right? So if you calculate this clearly, you can get approximately equal to 0. So that's how we can also say that V2F is basically 0. Okay. So basically what does it mean here? So let us say that M2 is a very, very high mass and M1 is coming as a velocity, and what will happen? This mass will just reverse its direction, move in this direction, and V2F will be again value of 0. So here the velocity will be 0 only in that direction. For velocity will be same but in opposite direction for V1I, and it will be equal to 0 for the second. Okay, let us assume something. Let us say a very let us take that we are a very big block of rock is being kept here, and some sort of ball is being rolling from this direction. Okay, and what will happen if a completely elastic collision is happening, and this rock will be in this place only, but this ball will go in the opposite direction. So that is the example here. Therefore, the heavier mass is undisturbed by the lighter mass reverses its velocity. Fine. Okay. So that thing being said, let's understand now a simple off-topic answer which is called as head-on collision. Okay. So that was a complete explanation of your two different parts. One was completely elastic collision and another was an elastic collision. Okay. Right. So in performing an experimental collision on a horizontal surface, we face three difficulties. So let us understand the difficulties here. So this is only as an experimental way. Theoretically, we can say everything, but what happens in experimental, what the difficulties we face in experimental is being understood. Okay. So one, there will be a friction and bodies will not travel with uniform velocities. It is quite evident. Why this happens? Because of friction. So because of friction, we cannot consider, or we cannot every time have these bodies to be going in some constant velocities, or basically uniform velocity. What does it mean by uniform velocity? That the amount of displacement delta is always same for each of the particular constant time interval delta. Okay. Fine. Moving on to what is the second difficulty? That if two bodies of different size collide on a table, it would be difficult to arrange them for a head-on collision unless their center of mass are at the same height above the surface. So what does it basically say? Let us suppose this is the ground level. Okay, let us suppose this is the ground level. Now what actually happens, you will understand about the concept center of masses in the chapter about center of this system of particles and rotation motion. But just to explain you, let us say, I'm just giving you for now only. Let us suppose you have this small mass and you have this big mass. Okay, the center of mass of this will lie at this location, and center of mass of this will lie at the center of this location. Okay, now for the head-on collision to occur, what is basically required? That the axis, so basically the collision should be head-on if the collision is some sort of distance in which the center of masses aligns with their let's say velocities, okay, or their movement. But actually in the ground level this cannot happen. Why this cannot happen? Let us understand. Because let us say you can watch this experiment in your day-to-day table also. So let's say you have kept your laptop on the table, right? And so on the same table, let us say you have a big ball, and let us say you have a small ball, right? The center of mass of this ball is here. Let us say it is going in this direction, and let us say the center of mass this is here. You can clearly see there is a difference. There is a difference in the distance of the center of mass from the for the two bodies here. Okay, and so that is the reason if this is happening, if this delta is present, then there is no head-on collision. This is not called a head-on collision. Okay, head-on collision only occurs when the direction of collision is basically along the center of mass. Okay, so that is the second difficulty here. Just iterating the second difficulty again. So if two bodies of different sizes collide on a table, it would be difficult to arrange them for a head-on collision unless their center of mass are at the same height above the surface. 3. It would be fairly difficult to measure velocity of the two bodies just before and after the collision. Very important. How can we measure the velocities exactly after the collision, before the collision? To take anything in front of you, try to measure the velocity. It's very difficult. So these are basically three difficulties. We're performing this experiment. So how is there any way in which these three difficulties can be removed? So the answer is here. So by performing this experiment in a vertical direction, so basically this is being done in a horizontal direction. Let us say we perform this experiment in a vertical direction, then all the three difficulties vanish. Okay. How it is vanished? Let us understand now using this example. Okay. Look at the figure here. So now let us understand what is happening here. So take two balls, one of which is heavier. Let us say this is the heavier ball, and the other lighter. Let us say this is the lighter. So the heavier can be either basketball, football, or volleyball, and the lighter can be either tennis ball, rubber ball, or table tennis. Okay. First, take only the heavier ball and drop it vertically from height, say 1 meter. Okay. So let us say we have took the heavier ball here. Okay, and we dropped it. simple free fall is happening. Note to which it rises. So basically, of the bouncing back of it, it will rise to some height. Let us say it rises to height some x. Okay. Now this gives the velocity near the floor or ground just before and just after the bounce. Okay. So basically, from the value. So now using simple kinematics here. Simple kinematics here. Let us say I had a ball here, correct, and it is being going to this ground. Okay. So using simple concept of kinematics, we know that final velocity v square is nothing but equal to 2g into h. H is 1 meter, right? Similarly, after the collision, let us say it is going with some velocity. So initial velocity is known now. That initial velocity, final velocity is 0 here, and the displacement is known. So again, what we can say? Again, we can say that velocity, this v dash is nothing but equal to 2g into that x. So therefore, we know the initial velocity also before the collision and with the final velocity also after the collision. So I hope this concept is clear. So therefore, this gives the velocity near the floor ground just before and after the bounce. Hence, you will get the coefficient of restitution. Coefficient of restitution is basically a topic. So basically, to get the efficiency of the velocity. Okay, so either it's the velocity ratio or basically it's the ratio. It is known by E actually. It is known by E. So that coefficient of restitution tells you the amount of loss happened when the collision has happened. So basically, it's a relative measure to calculate or to measure whether a collision is elastic, inelastic, or completely inelastic. Okay. Now take the big ball and the small ball and hold them in your hands one over the other. So let us take with one hand I kept it here, and let us say with the other hand I kept it here. Okay. With the heavier ball below the lighter one as shown. So let us say I keep the ball in this case scenario like this and drop them together, taking care that they remain together while falling. So basically, this is how the free fall would happen now. If the free fall happens like this, you will find that the heavier ball rises less than when it was dropped alone, while the lighter one shoots about 3 meters. Okay, so let us suppose this is the initial way in which the balls were being kept. What happens after the collision? That the bigger, heavier ball is here only, while the shorter ball shoots upwards. With practice, you will be able to hold the ball properly so that the lighter ball rises vertically up and does not fly sideways. Okay, so this is just a fact given to you that there may be chances that if it is not aligned properly, the direction of the movement of the balls can be inwards or outwards. So if you again and again practice, again and again do this experiment, you will find a way in which you can find in which both of these balls are going in vertical direction. This is basically a simple example of doing a head-on collision. Okay, so you can try to find the best combination of balls which gives you the best effect. Okay, so now if you remember correctly, the difficulties which we offered, the first difficulty which was offered was friction. Okay, so if you see clearly, this is nothing but a simple example of a free fall happening. Correct. So the effect of friction is being removed here. Right. So first difficulty is directly removed. Similarly, let's understand the second difficulty here. The second difficulty was regarding head-on collision happening. Okay, so basically the center of mass of both should be aligned. If you see clearly, the center of mass are clearly aligned. Okay, so if the experiment is complete in which the direction of movement of the collision is in upward direction, exactly vertical, then it is quite clear that a head-on collision is the center of mass are clearly aligned in the vertical direction. So that means that the second difficulty is also completed. Okay. Now second difficulty is also resolved. Now let us understand the third difficulty. What was the third difficulty? The third difficulty was simply that it is fairly difficult to measure velocities of the two bodies just before and after the collision. So I hope you can understand that this third difficulty is also resolved. How? So what we will do basically here, let us understand from this scenario. In this scenario, what will happen? So we know that initial velocity v1i is also 0, and here it will not be v1i, with some v only. So this v is 0 here, this v is also 0. Okay. We know the height for this, which is some, let's say h1. We know the height for this, which is some h2. Okay. So we can calculate that the initial value of v1i is nothing but equal to under root of 2g h1. And similarly, what is v2i? V2R will be nothing but under root of 2GH2. Let us suppose after the collision happening, this big ball only reaches a height h3, and this small ball reaches a height h. Therefore, now we have V1F is nothing but equal to under root 2GH3, and we also have V2F is equal to under root 2GH. Okay, so I hope we understood how to calculate the velocities also after basically the initial and the final velocities before collision and after collision. Okay, so that is how head-on collision occurs, and we can resolve basically we have resolved all the three difficulties. Okay, so that thing being said, so let us understand one typical example. We will just understand the basics of this. We won't go into detailing. So because it's a question regarding a nuclear energy. Okay, so I will just try to make you understand the example, and then we can move forward. So basically, slowing down of neutrons. So the subatomic particles also consider some sort of collisions happening, which is one example is given. So in a nuclear reactor, a neutron of high speed, namely typically 10 to the power 7 meter per second, must be slowed to 10 to the power 3 meter per second, so that it can have a high probability of interacting with isotope. Okay, so basically for the nuclear reaction to occur, we want that this neutron should be decreased, there should be a decrease in its speed. Okay, so that fission can occur. Okay, show that a neutron can lose most of its kinetic energy in an elastic collision with a light nuclei like deuterium or carbon, which has a mass of only few times a neutron. So basically they are saying, let us suppose this is some neutron, and let us say this is some deuterium. So basically they are saying that let us suppose a collision between both of this is happening, then we can basically decrease the velocity of this so that fission can occur. So I hope the question is clear to you. So the material making up the nuclei is basically D2O or graphite, which is called as moderator. So this moderator is being used basically decrease the value of velocity of your neutron. Okay. Right. So let's go very slowly. So first of all, what is the initial kinetic energy of the neutron? It is nothing but half into m1 into v1I square. Right? What is the final kinetic energy? Final kinetic energy of the neutron. We just calculated it before also, because when an elastic collision was happening, it is nothing but half m1 into v1f square, and v1f value we have already calculated before. What it was? It was nothing but equal to m1 minus m2 upon m1 plus m2 into v1 square. Okay, if we just put it here, what is the fractional kinetic energy lost? So it's just a term to understand the complete discussion. Okay, so F1 is basically K1F upon K1. So what we just did, we just divided the equation number 2 with equation number 1. It leads us to the equation which is F1, which is equal to M1 minus M2 upon M1 plus M2 whole square. So just dividing equation 2 with 1. Okay, fine. While the fractional kinetic energy gained by the moderating nuclei, that is K2F by K1I, is basically F2. Okay, so you will understand basically in your further discussions, you will also understand in your nuclear energy concepts. Okay, that the fractional energy gained by something is equal to plus the fractional energy lost by something is equal to 1. Okay, so that's why it's a simple fact which we need to understand. Therefore, we can directly write F1 plus F2 is equal to 1, or we can also write F2 is equal to 1 minus F. Okay, so the gain by something is equal to the gain by something plus lost by something is basically equal to 1. Okay, so hence 1 minus F1, we just calculated the F1 value here. Therefore, simple mathematical calculations gives us the value of F2 as 4 m1 m2 upon m1 plus m2 whole square. Okay, so now we know that what for deuterium, the mass m2 is basically twice the mass of this neutron. Okay, so therefore just putting the results here. So what we are doing basically, we're just putting m2 is equal to 2m1 here, and similarly here also we are putting m2 is equal to 2m. If you put those values, we will basically get f1 is 1 by 9 and f2 is 8 by 9. What we can understand from here? We can understand that almost 90% of the neutron's energy is transferred to it. Okay, so basically it was having 10 to the power 7 meter per second. It has been now below 10 to the power 3 meter per second. Why? Because let's say it was 100% energy. As 90% is being lost, so it is only happening, it is not only having 10% of the energy. Okay, so for carbon, now this is just a fact given to you. So for carbon, F1 is 71.6% and F2 is 28.4%. In practice, however, this number is smaller since head-on collisions are rare. Okay, so there is no technicality involved here. Let's not go into technicality. Let us understand the concept we are trying to understand here, which is collision. So basically, the crux which we directly implemented was just this thing, that it's an elastic collision. First of all, the first concept. So basically, we use the formula directly of V1F and V2. Okay, that is M1 minus M2 upon M1 plus M2 into V1I. And similarly, V2F is 2M1 upon M1 plus M2 into V2. Okay. So that's the final concept, and then we can move on to the final discussion about your collisions in two dimensions. Okay. So the initial velocities and the final velocities of both the bodies are along the same straight line, which was basically happened till now. Then it is called as a one-dimensional collision or head-on collision. Also remember that the center of masses of both should be same for the head-on collision to occur. They will also get its difficulty when we are understanding about the head-on collision. In the case of small spherical bodies, this is possible if the direction of travel of body 1 passes to the center of body 2, which is at rest. So they are just saying that the center of mass of both of them, or basically for the center of body of sphere is basically also called a center of mass. We will understand very clearly the concept of center of mass in the chapter system of rotation, system of particles and rotation. For just now, you can understand that center of mass for a sphere is basically at the center. Okay, so this should lie along this particular axis when we join the two. Okay, so head-on collision is only possible in this. Okay. In general, the collision is two-dimensional, where the initial velocities and final velocities line up. So in general, what happens? That collision are not in every sense it is only one dimension, because head-on collisions are very rare, because many parameters have to be adjusted, or basically many assumptions have to be taken for head-on collision to occur. So in general, the collision is two-dimensional, where the initial velocities and the final velocities lie in a. Okay. So that thing being said, let us understand the final discussion of this chapter, which is collisions in two dimensions. Okay. So figure shows figure shown here depicts a collision of a moving mass m1 with the stationary mass m2. Linear momentum is conserved in such a collision. Since momentum is a vector, that implies three equations for three dimensions. Okay, so here momentum is a vector, implying that three equations are in three dimensions. So basically what we can say, we can conserve the linear momentum in this direction also, we can conserve the linear momentum in this direction also, and we can conserve the linear momentum in this direction also. Okay. Consider the plane determined by the final velocity directions of m1 and m2 and choose it to be xy plane. What we are understanding here, let us understand that this collision is occurring in the 2D plane of xy axis. So basically, even if we consider or even if we conserve the momentums in x and y direction only, our questions will be resolved directly. There is no use to conserve, or basically when we try to conserve it in z direction, there is no use, because the answer in the left hand side and right hand side would come out to be 0. Okay. So that thing being said, let us first understand what is the conservation of momentum here. For the conservation of momentum, the z component of linear momentum implies that entire collision is in xy plane. So let us now calculate the x and y component equations for momentum. Okay. So if you see clearly, before collision, this is mass m1, this is mass m2. Okay, so what is the initial momentum? It's m1 v1i plus m2 v2i. This is having some velocity v1i, and this is having some velocity which is 0. And the initial momentum is m1 v1i. Okay, in the x direction. We are talking about only x direction. So I hope that is also clear to you. Now let us calculate the same thing for x direction after collision. So what will happen after collision? So let us say this is at m1. We just need to resolve this value of velocity v1f in this direction. And similarly, resolve this value of velocity in this direction of x-axis. Therefore, this will be nothing but m1 v1f cos theta 1 plus m2 v2f cos theta 2. So I hope the resolution is clear to you. So in this direction, it will be v1f cos theta 1 and this will be equal to v2f cos theta 2. In this direction and this direction, this will be equal to v1f sin theta 1 and in negative direction, it will be v2f sin theta 2. Okay. So I hope the equation number 1 is clear to you. So therefore, m1 v1i is nothing but equal to m1 v1f cos theta 1 plus m2 v2f cos theta 2. Now let's understand it for the conservation of momentum for second, that is y direction. What happens in y direction? The initial velocity or the initial momentum along the y direction is 0 because there is no velocity in this direction. Therefore, this will be 0, which is equal to, see clearly, it is in positive sense, it is in negative sense, it is going downwards, correct? Therefore, we will write m1 v1f sin theta 1 minus m2 v2f sin theta. Okay, so I hope this concept is clear to you. So therefore, we obtained the conservation of momentum in the x and y direction. Okay, so one knows m1, m2 and v1i only. There are thus 4 unknowns. What are the 4 unknowns? It is v1f value, it is v2f value, this value of theta 1 and this value of theta 2. Okay, so there are 4 unknowns. We have 4 unknowns and only 2 equations. If theta 1 and theta 2 is 0, that is the case in x direction, then we basically regain the equation for one dimension consolidation. So then it is okay because then we have basically resolved. This is the thing which I have already completed. That is collision in one dimension. We are trying here to do collisions in 2 dimensions. Okay. Now further, if the collision is elastic, then basically we can conserve the momentum. Conserve the energy also. Please remember this very, very carefully. If in the question it is given that the collision is elastic, then only you can conserve the energy. If it is given that the collision is inelastic or completely inelastic, there will be loss in kinetic energy. Okay. So because the collision is elastic, we can say that the initial kinetic energy, that is half m1 v1i square, is equal to final kinetic energy of the both terms. So it's half m1 v1f square plus half m2 v2f square. Okay. So therefore now we obtained one more equation. So we have now 4 unknowns and 3 equations. This still leaves us one equation short. At least one of the 4 unknowns, say theta 1, must be made known for the problem to be solved. So by some way or the another, if we can understand, let's say we have some angle measuring device so that we can, and one unknown is already given to us in the question, then we can solve collision in 2 dimensions. Otherwise it is difficult or it is not possible to solve the collision in 2 dimensions. Okay. For example, theta 1 can be determined by moving a detector in angular fashion from the x to y axis. So given that we have m1, m2, v1 and theta 1, we can determine these 3 from the 3 equations given. So what are the 3 equations? This is your first equation, this is your second equation, and this is your third equation. Okay, so 3 equations, 3 unknowns, if one of them is given. Okay. So that being said, let us understand one of these simple example of your collision in 2 dimensions and then move forward. Okay. So consider the collision depicted in the figure to be between 2 billiard balls, so which are having equal masses. So it is first of all given in the question that m1 is basically equal to m2. Okay. The first ball is called a cue ball while the second ball is called as the target. So this is basically a cue ball and this is basically a target ball. Okay. Next is the billiard ball. A player wants to sink the target ball in the corner pocket. So he wants to hit it such a way that this target ball goes inside the hole. We want to sink the target ball in the corner pocket, which is at an angle of, let us say, okay, so let's not make it in this direction. Let us make it in this direction, that it went in this direction with an angle of, let's say, 37 degrees, and there was a hole here. Okay, so this was basically a hole. Okay, assume that the collision is elastic. Please understand this. If it is said that the collision is elastic, that means we can apply the conservation of energy, and that friction and rotational motion are not important. That means there is no loss in energy due to friction or rotational motion is not happening. So only the question answers, you need to obtain the value of theta. Okay, so what we will do, we will apply the conservation of energy, we will apply the conservation of momentum and solve the question. Okay, fine. So let's move forward. Let us first calculate the equation number 1. That is, for momentum conservation, we can directly write v1i is equal to v1f plus v2f. So in similar sense, which we did before. Now let's understand this. And this is the first equation, and this is your energy conservation equation. That is, v1i square is equal to v1f plus v2f dot v1f dot v2f. Okay. Solving this, so basically what we are doing is, in simple form, what we are doing is, we are just using this as equation number 1, this as equation number 2, and this as equation number 3. And finally, what we are doing, moreover, this value of theta 2 is given to us in the question. Okay, and basically we are calculating this theta. Okay, so that means that leaves us directly with the equation, that is v1i square. v1i square is nothing but equal to v1f square plus v2f square plus 2f1 v2f cos theta 1 plus 36. Since the collision is elastic, m1 is equal to m2, and therefore finally we got v1i square is equal to v1f square plus v2f. So therefore that equation can only be valid. That means this equation number 3 and this equation number 4 is same, correct? So this is only and only valid, and this value will be equal to 0. So if this value is equal to 0, what we can basically say, that theta 1 plus 37 is 90, and hence we can say that theta 1 is 53 degrees. This is a very important concept. This question is involved here so that we can understand one more discussion regarding this. So what happens, please see clearly. Please understand the last line very clearly. This proves a following result. What is that result? The result simply states that when two equal masses undergo a glancing elastic collision with one of them at rest, and m1 is equal to m2, after the collision, they will move at right angles to each other. So basically, they are saying that this angle is 90 degrees. When what are the property assumptions being done here, or what are the things we need to remember? First of all, m1 is equal to m2 here. Second thing, that v2i should be 0 here. And third thing is collision should be elastic. So if these three properties are happening, then you can directly, if one value of theta 1 is given, so you can directly calculate the value of theta 2. So that is the basic reason why this example is being added up here. That thing being said, let's move forward and understand some more discussions and then close this complete chapter. Okay. The matter simplifies greatly if we consider spherical masses with smooth surface and assume that collision takes place only when bodies touch each other. This is what happens in the games of marbles, caroms, and billiards. In our everyday world, collisions take place only when two bodies touch each other. But consider a comet coming from far distances to the sun, or alpha particle coming towards the nucleus and going away in some direction. So in general physical sense, it is okay that we can define something that collision can occur when? It can occur only when the two bodies touch each other. But can we consider these examples also as collisions or not? These examples can also be considered as collision, but these explanation or the calculations involved in this are some sort of difference as we do in actually in physics. We won't be studying that concepts here. This is just to inform you that everyday bigger concepts or some concepts cannot be directly implemented using the concept which you have understood in this complete lecture. There are many things which are far beyond this complete concept also. If you have interest in this, you can just understand more in the future classes. So here we have to deal with forces involving action at a distance, which is an event which is called a scatter. The velocities and directions in which the two particles go away depend on their initial velocities as well as the types of interaction between them, their masses, shapes, and sizes. Okay, so you will understand more about this. Then let us say there is in chemistry also. If you have went on to till that topics, you may have understood something called as hydrogen bond, covalent bond, then coordinate bonds, etc. So the purpose of collisions may be happening in that sequences also, or between that atoms and molecules also, but the collisions cannot be directly implemented based upon only the assumption that m2 is equal, velocity of p2 is 0 and m1 is 0. Only the concept of elasticity can be used up there. There are many more projections applying there. Let us say an electric field is happening here. You will understand what electric field in subsequent lectures, subsequent chapters, and the complete understanding or complete formulation of this question changes. Fine. So that is just a simple heads up for you so that you can understand that everything till now is being worked upon on assumptions only. We'll move forward with majority of the things. So till now, as far as your class 11, class 12 is considered, this amount of understanding of collisions is appropriate so that we can basically solve basic kinematic questions. Just the final 2-3 points which you need to understand is that if the question asks is regarding your collision with elastic, do apply the conservation of energy, but if it is inelastic or completely inelastic, you cannot apply that conservation of energy. Conservation of momentum is always applicable. In one dimension, it will be one equation only. In two dimensions, there will be two different equations, one in x direction, one in y direction. Okay. So that thing being said, let me just close the discussion. So that is the complete end of your chapter work, energy, and power. So we started with the introduction in which we understood basically about the scalar dot product. So in scalar dot product, we understood basically that A dot B is nothing but equal to AB cos theta. Here cos theta is the angle between them, right? This is a scalar product, right? And we understood some of the properties such as commutative and the distributive properties. And we understood in work energy theorem that delta K is basically equal to half mv square final minus velocity final minus half mv velocity initial squared, which is equal to work done. And work done, we understood that work done is nothing but equal to F dot D, which is equal to Fd cos theta. In kinetic energy, we understood this, that energy is nothing but equal to half mv square. In work done by variable force, till all these points, we understood force has some constant value, but here we understood force has some value which changes the displacement. Then in the work energy theorem for a variable force, we understood that work done is nothing but equal to integration xi to xf f of x dx. Okay, which is equal to nothing but kf minus k. Then you understood the concept of potential energy. So for concept of potential energy, we understood the conservative forces and non-conservative forces also. For gravitational potential energy, we calculated this value to be equal to mg. And we understood the conservation of mechanical energy, that the mechanical energy is always constant if we are talking about the conservative forces. And we understood the potential energy of spring, where Fs is basically minus kx, where k is a spring constant, and potential energy is basically equal to half k x square. Then we understood various forms of energy such as heat, chemical, electrical, nuclear energy. We also understood about Einstein's equation, that is equal to E equal to mc square. Okay, and we understood about power, that is nothing but work per unit time. We also understood about horsepower, which is equal to 746 watts. We did some of the questions regarding it. We also understood kilowatt hour, that is the amount of how the energy is being calculated, which is being used in our homes or day-to-day appliances. And finally, in the last concept, we understood about collision. First in one dimension, then in sec 2 dimension. Also understood a concept called elastic and inelastic collision. Fine. So that thing being said, that is the end of this complete discussion. So thank you for listening to this lecture. So just a quick brief of where we are standing right now. So we started with something called the units and measurements, in which we basically understood what are SI units, whatever do we need to use in our day-to-day physics appliances. Then we went on to understand next chapter, which was motion in a straight line, in which we understood basically kinematics equation, right? Then we understood basically this was basically in one dimension. And we increased our dimensional space. We went on to understand this in a plane. That is basically x and y axis. Then after this was being done, in this we also understood uniform circular motion. Then we understood next chapter regarding our laws of motion, in which we understood the Newton's laws of motion. We understood FBT diagrams in this. And now we understood a chapter which is work, energy and power. So right now, till this is your basically kinematics, which is done. I think after this, we will understand a new chapter, basically, which is rotational motion. So we will understand about rotational motion. Okay. So that thing being said, thank you for listening for this lecture. We will meet soon with some another chapter. So thank you so much.